In this video, we're going to actually look at subgroups of cyclic groups, which is interesting. And we're going to completely classify what they look like. A subgroup G is cyclic if G is of the form is a cyclic subgroup generated by little g for some little g that's an element. In other words, if your group can be generated by one element. For instance, the integers are a cyclic group, as are the integers modulo n. So let's look at subgroups of cyclic groups. I'm going to use little a instead of little g, so it's easier to talk about. Let's let H just be some subgroup of a cyclic group generated by A. In particular, H is a collection of powers of A. So instead of talking, as I have in previous videos, about letting X be in H, and then saying, well, then X is equal to A to the n for some n, I'm sometimes going to get a little bit careless for now and just say A to the n's in H. When we go back to proofs, I'm going to go back to being careful. But for this discussion, let's just be a little more carefree. So suppose A to the n is in H. Then, because you're closed under exponentiation, A to the mn is in H for all m. So in particular, the cyclic subgroup generated by A to the n is a subgroup of H. So H contains cyclic subgroups as well. Okay, that's not that surprising. But let's look at A to the n, A to the m, both elements of H, and let's suppose for a moment that m is less than n. Well, then A to the n minus m is also in H. Why? Because it's A to the n times A to the negative 1 to the mth power. And H is a subgroup, so H is closed under inversion, which you could rewrite this as am to the negative 1. N is closed under multiplication. And why do I say this? Well, what else can you get in here? If I rewrite n using long division, I can rewrite n as a quotient times m plus some remainder term. And by this logic, A to the n minus q times m is also in H. So A to the r is in H. So starting with two elements in H, I end up with a third element in H whose exponent is smaller. Let's assume for right now that I'm talking about positive integers to make life a little easier. And so if I use the fact that AM and AR are both in H, I can continue this same line of reasoning. R is less than M, so I can do long division with quotients and remainders, and I can rewrite M as a Q prime R plus some S, and I can discover that A to the S is in H. And you can see where this is going, maybe, but if not, what I'm getting at is if you apply the Euclidean algorithm, then what we've just discovered is that if I let D be the GCD of n and m, then in fact A to the D is an element of H. So the punchline there is that I managed to get the GCD to be an element of H. And the reason why that's important is because, of course, A to the n is in the cyclic subgroup generated by A to the D, as is A to the m, because m and n are both multiples of D. And so given two arbitrary elements in H, I actually found out that they are both multiples of some other element in H. That's kind of quirky. And so maybe you could start to see where I'm headed with this discovery. Suppose instead I actually had a whole bunch of numbers, a to the n1, a to the n2, a to the nk, all elements in H. By doing this process of elimination two at a time, I could get a smaller list of elements in H, etc., until I finally get to one ultimate element with the property that everything in this original list is just a power of this one. So in other words, it starts to look like every single element in H is just a power of one element in H, which suggests that H is cyclic. Note, this might not be true because right now this argument is talking about finite subsets of elements. But it turns out the conjecture I'm making actually is true. And so this discussion so far was to try to motivate how one might have been led to this result in the first place. So here's the theorem. Every subgroup of a cyclic group is cyclic. Well, let's try to prove it. Let G be a cyclic group. Let A be the generator, and let H be a subgroup. What do we want to show? H is cyclic, which means we want to show H is the form angle brackets X for some X and G. Remember, G is powers of A. And so since X is an element of G, it must be the case that X is just some power of K. So the only question in order to finish this proof is to figure out which power should we pick. Well, I guess an educated guess is how about the smallest positive power? So the smallest positive power, K, such that A to the K is actually an element of H. So let's make that attempt. Let K be the smallest positive integer, such that A to the K is an element of H. We have to make some sort of argument that such a K actually exists. In other words, that there are in fact positive integer powers such that A to the K is an element of H. So, well, suppose A to the R were an element of H for some R less than 0, then A to the negative R was an H. So the set of positive integers where A to the K is an H must be non-empty. My point here is that if you had a negative power that lands in H, then using inversion gives you a positive power that lands in H. So you must have positive powers, and so K must be well defined. Except there's this little caveat here. Here we're assuming that there was a negative power. What if you don't have positive or negative powers? Well, that means that H is the trivial subgroup. Alright, so as an edit, let's add in the assumption that H is not trivial. If H is the trivial subgroup, then we've already discussed before that the trivial subgroup is the cyclic subgroup generated by E, and the result is already proven. So we're not really making the proof much more complicated. But because it's a non-trivial thing, it must contain a positive or negative power. If it contains a negative power, by this result it contains positive powers. So, K is in fact well defined. And the smallest such K must exist. Okay then, what do we want to claim? That the cyclic subgroup generated by A to the K is in fact in H. Well, as we've already discussed earlier, since A to the K is an element of H, the cyclic subgroup generated by A to the K must be a subgroup of H. By definition of cyclic subgroup, it's the smallest subgroup containing that element. So the only thing we need to show is that every element of H is in fact a power of a to the k. So now we just try to brainstorm for a moment. You take an element in H. H is a subset of powers of A, so X must be of the form a to the m. What do we need? We need it to be of the form a to the qk for some q. Or I should say a to the k to the q, which is a to the qk. Well, we have m. We want it to be of this form, so it better be the case that m is equal to q times k. Well, how do we solve for q? Well, that's a little tricky. We can't just divide, because then we're actually assuming that q exists and is an integer. The only thing we can say for sure is that we can write m equals qk plus r by the division algorithm. That's the only thing we know for sure. So then we just need to argue that r is 0. If we can argue that r is 0, then we got what we wanted. Now let's write down what we discussed more formally. Let x be an element of H. Then x is in this cyclic subgroup, so x is a power of A for some integer power m. By the division algorithm, m has a quotient and a remainder. The quotient and remainder are integers, and r is between 0 and k, the divisor. So x is equal a to the qk plus r. So of course, where do we want to go from here? Well, we want to get rid of the r. We think out loud, how can we do that? Well, let's just use properties of exponents for now. We can rewrite it like that. We have a to the k to the qth power times a to the r. Well, we can multiply by a to the negative qk on both sides. If we want to, because we know that's an element in H already, and then we get a to the r as an element in H, with r less than k, which means we now found and r is greater than or equal to 0. So to make the conclusion a little more understandable, suppose k were, say, 5, and suppose that the r we came up with was 3. So 5 is saying that a to the 5th power is the smallest positive integer power that lies in H. What we just discovered was that a cubed is also in H. Clearly that's a contradiction. So if the 5th power is the smallest positive power that lies in H, you can't get a cube. So it must be the case that r is 0. So let's write this more formally again. X is equal to a to the qk times a to the r. So if I multiply through by a to the k to the negative q times x, I get the cancellation here, which gives me an element in H. Because H is a subgroup, x is in H, a to the k is in H. So properties of exponentials, this power of a to the k is also in H, and this product is also in H. And by definition of k is the smallest positive integer power, such that a to the k is in H, and by definition of r being a number between 0 and k, we see that if a to the r is in H, r is strictly less than k, r has to be 0. So r is 0, which means that this is a to the 0 as the identity element. Congratulations, x is equal to a to the k to the q. So x is equal to a to the qk, which is the qth power of a to the k, which means x is in this cyclic subgroup, which gives us the reverse inclusion, that H is a subset of this cyclic subgroup. Therefore, we have equality. As a simple corollary, every subgroup of the integers is of the form m times z, where m is a natural number. Remember, m times z is the set of multiples of m. So using this theorem allows us to classify all subgroups of the integers as an additive group. So this is under addition. Why? Because we already pointed out z is cyclic, which means by the previous theorem, every subgroup of z is cyclic, which means it must be generated by some element, like m. And since we're writing additively, powers are really multiples. So instead of g to the n, it's m times n, as n runs over all integers. But that's the definition of m times z. So congratulations, from this really abstract theorem, we managed to get this really concrete result, that we actually know what all subgroups of the integers look like. So in particular, the set of powers of 2 is not going to be a subgroup under addition, nor will the set of all odd integers when you just add 0 to it, or any